All right, today is our last topic for Chapter 16, and it's on fission and fusion. Both of these are nuclear reactions that occur to produce energy. And over the course of history, nuclear power and nuclear power plants have scared quite a few people away. But in general, it's typically quite safe and probably a lot cleaner than our typical power plants that we use around here where we burn coal. So what we're going to do is we're going to figure out first what they are, and then we're going to look at one in each of them independently to kind of see how they work and how the reactions would work for that. So first off, fission is where we take a large atomic element, so we have something like uranium or something like that, and then we're going to split it into smaller elements, smaller nucleuses, and in that process we release some energy. So typically what happens is we start with something like uranium-238, and we add 238, and we add a neutron, which would be 0, 1. So if we add a neutron to something like uranium, what typically it happens is it becomes really unstable, and once it's unstable, it then undergoes a reaction, an alpha, gamma, whatever. It undergoes some sort of reaction which releases power. And in general, fission is fairly easy to do. We can make these reactions quite simply, and we actually get quite a bit of power out of it. The problem is the byproducts, the elements that are created after the reaction, tend to be quite toxic, so we get lots of nuclear waste that has to be stored for thousands of years before it decays enough to be safe. So that's the biggest issue. Fusion, on the other hand, is sort of the opposite. We're taking two smaller elements, so that'd be like taking hydrogen atoms and adding them together, and they would form something like helium. Or we could take, say, hydrogen and oxygen, and maybe we get something like water or whatever. So it's taking smaller nucleus items and merging them together, and by fusing them together, that's going to give off a certain amount of energy as well. This is a process that our sun does, so when we get heat and light from our sun, it's due to fusion. And so far in history, we can actually do this okay in a lab situation. We could actually create energy by fusion. The problem is, at this point, it takes more energy to create the heat and the power that's needed to make these things fuse together than what we actually get out of it. So the problem is it's not feasible to put more energy than you're getting out. And the pros, definitely, obviously, we get nice, safe, easy to handle chemicals in the byproduct. So we'll start with fission because it's the most common, and this is what all of our power plants and things use. So we'll first of all understand how this works, and then we'll look at fusion briefly afterwards. So fission, typically the most common chemical we're using to start with is uranium-235, and it just comes from some Germans in 1939. They found out that if you take uranium-235 and add a neutron to it, make it uranium-236, that 236 is extremely unstable, and it almost instantly splits into smaller atoms. And what happens is we actually get two different types of reactions, and they happen about 50% each. So uranium-235, you can see in this first one, we add one neutron to it, it becomes uranium-236, and then instantly it splits into 141 barium and 92 krypton. And if we balance our numbers, if we have 141 plus 92, that gives us 233. And if we balance the bottom numbers, they do add up to 92, so that's good. But basically, we're short 3 neutrons. So what happens is we get extra 3 neutrons ejected. So we take uranium-235, add 1 neutron, we get 2 different chemicals, and 3 extra neutrons get created. And then it also releases a certain amount of energy that gets used. The other reaction is almost the same, except it changes into xenon and strontium, and then it only releases 2 neutrons. So out of the 2 reactions, we both get extra neutrons, and we both get extra energy created. So at any point in any of these reactions, you're going to get one or the other, and like I said, they're roughly about 50% of the time each. So quite often what we do is we just call it element X and Y. It doesn't really matter which 2 we get, and we get, on average, 2.5 neutrons emitted. So the question then is, if we add 1 neutron to the initial reaction, and we get these other chemicals plus, on average, 2.5 neutrons, what do we do with those extra 2.5? Obviously, we need to do more reactions. Like this is only for 1 nucleus, so we need to do more and more. So where do we get that extra neutron that we need to do the reactions? Well, we can either add it again, which is going to require energy, or what ends up happening is we take some of those 2.5 extra neutrons and put them back into the reaction chamber to start all over again. So you can see here, we call this a critical reaction. So we start with 1 neutron in the uranium-235, that produces our extras. We then take one of those, add it to another nucleus, that creates another reaction. We take another one of those, add it again, another one of those, add it again, and so on. The cycle goes on. And it'll basically continue forever as long as we keep adding 1 extra neutron and as long as we have enough uranium to react with. So we might just have to keep adding uranium to the nuclear reactor. So we call this critical. So critical is where the numbers are balancing. We're adding 1, we're adding 1, we create 2.5, we take 1 to add another one to create more, take another one, create more, take another one, create more, and so on. If we added all 2.5, what's going to happen is we're going to get an exponential reaction. So if we took 2 neutrons, and you can see in this diagram, if we took 2 and put them both back in, they would create 2 more, and so on. So we'd end up getting this exponential growth, which we call this supercritical. So that means our reactions are getting bigger and bigger. We get more and more reactions exponentially. Sometimes this is good. So in a nuclear bomb, that's what we want to do. We want one reaction to kick off millions of them within a split second, and that's what the bomb then explodes. When a nuclear power plant first starts, we want it to be supercritical to get it up to speed, to get it towards producing enough energy. But we don't want it to happen when a nuclear power plant is already at its peak. If we want it to keep going, then we just want to make it back to critical. We want to keep it stable. So if it keeps going supercritical, then eventually it's going to explode like a bomb would as well. And that's what happened in Chernobyl when the power plant exploded. And it almost happened in Tokyo a few years ago with the tsunami. They had trouble getting it back to a critical level. It was going supercritical and they couldn't slow it down. So all of a sudden, what would happen if we didn't send the neutrons? So if that 1 extra neutron didn't go back to the reaction, then we're going to basically cancel it. We'll create the extra neutrons, but if we don't send them back, then we would call it subcritical. So that means is the reactions are going to start to slow down, and eventually they would stop, and that's what we do to shut down a reactor. So if they say we're going to go under shutdown, they basically cancel those reactions so that eventually it stops. So the question then is, how do we control whether it's critical, supercritical, subcritical, and so on? And the idea is, well, we just have to control how many neutrons go back in. So if we take those 2 or 3 neutrons, we need to get rid of the leftovers. So let's suppose we only want 1 to come out of a reaction that produces 3. We'll send 1 back in, and we need to get rid of the other 2. So they use a control rod, which is basically just a long rod of material that absorbs a neutron. So if we have a neutron coming along, it hits the rod, it absorbs it, and it goes away. So quite often we use things like boron and cadmium because they're pretty good at absorbing neutrons, and all they do is they just basically raise or lower the rods to hit more or less neutrons. So if we don't want any neutrons to be collected, we just raise the rods right out so the neutrons just keep on going by and they miss the rods. If we want to slow down more of them, we drop them down so that as these neutrons come across, more of them get absorbed by those control rods. So it's just sort of like, think of it like fingers going up and down to collect all those extra neutrons that they want to get rid of. But there's still a couple of problems that they have to figure out. First of all, these neutrons that are being ejected are coming out at extremely fast rates, and they're actually too fast to be absorbed by the uranium, and they're too fast to be absorbed by the rods. So what we have to do is we have to slow them down somehow. So what they do basically is we need to put some sort of moderator in front of it to slow it down. We want to basically create a collision to get that neutron to slow down. So the best way to slow something down is put something pretty big in front of it. So we can't get neutrons very easily from other sources without adding a lot of energy, so that's not a good idea. So we want to pick something that's about the same size of a neutron, which is a proton, and a cheap source of protons is water. So basically what we do then is we just shoot the neutrons into a water tank, so that'll slow them down, and then we have our control rods that go inside the water tank to absorb the ones that we want to get rid of. And then the ones that make it through the water are going slow enough that they can go back into the reactor to start all over again. So that seems to work good, as we can use water to slow it down, but now the problem is sometimes the water will gain at these extra neutrons, and it ends up changing it to hydrogen 2, which we call deuterium. And basically what ends up happening is these water molecules have an extra neutron, and if they have an extra neutron, they end up becoming heavier. They're like double the mass, so we often call it heavy water. And the problem with heavy water is it can be toxic, so if we just dump that back into a river or whatever, it causes some environmental problems. So then the issue is, if we have heavy water, then what do we do with it afterwards? So there are three main solutions that solve this issue. The first is, in the United States, what they do is they use enriched uranium. So that just means they refine it more carefully so that the critical reactions have a better chance and the neutrons don't make as much heavy water. So they use a different uranium to start with. There's less neutrons being ejected, therefore the water stays fairly clean. It still heats up, which when they dump it into a river or a lake, that causes problems too, but in general it's safer. The other option is what Canada typically does, is they use heavy water in the reactor. So instead of starting with regular water, they intentionally put in heavy water, which basically won't absorb anymore. So they'll basically take heavy water and just keep reusing it. The neutrons don't get absorbed by the water, and they just go to the control rods, and that's it. So that's why in Canada we tend to be sort of leading in this industry, because we're not putting as much pollution back into the environment. And the last option is sort of the old-fashioned version, and what they found out was if they use graphite rods instead of boron or whatever, the graphite tends to absorb all the neutrons, so the water stays clean. But the problem is graphite is very explosive if it's exposed to oxygen. So what happens is, if the graphite absorbs the neutrons, that's great, but for whatever reason, if we get any oxygen in the system or we get some sort of explosion, these graphite rods turn into basically bombs themselves and cause lots of problems. And that's exactly what happened in Chernobyl. The carbon rods that they were using ignited. So that's it for fission. So fission works well in terms of making it able to work. We can control to get how much power we want out of it. That's a good thing, but the downside is the byproducts of the leftover chemicals plus the heavy water, those cause some issues. So ideally then, we'd like to switch to fusion. So fusion, like I said before, was made from smaller elements that merge together into something safe, and that merging process releases energy. So you can kind of see what happens here. We got two protons, they merge together into a new element. That gives off some energy and an antineutrino. Then we merge it again, we merge it again, we merge it again. We just keep doing this process to get more and more energy. So why don't we just use this all the time? Well, we haven't figured it out yet to be efficient. So we can build reactors, but it costs more energy than it is to come out. And the reason for that is we need lots of heat and lots of pressure to be able to fuse these things together. So the electricity and the heat that's needed to make it happen costs more than the amount of energy that we're actually producing. So a modern area of physics right now then is to create cold fusion. So the idea is to be able to do this without the intense heat, and then hopefully that'll make it more efficient to do. And that's pretty much it. So we're looking at the two different types, fission and fusion. In general, fusion creates more energy. So like one typical reaction would be in the neighborhood of 200 mega electron volts as the byproduct. And for fusion, we typically get energy levels for one fusion reaction, we end up getting about 17. So you can see it's quite a bit less. So that's some of the problems. So if we can get the energy requirement lower, so if we only have to spend 5 or 6 mega electron volts to get 17, then it would be profitable, then it would be worthwhile to do. Where with fission, we don't need to put much in and we get 200 coming out. So that's why most of the power plants around the world that are nuclear tend to use fission. And that's all for today.